let's just give everyone, all those thousands of people, give them a few minutes to, or a few seconds to drop on in. Not quite ready to rock and roll just yet. Just give everyone a chance. All right, that should be enough time, so let's get this show on the road. All right, greetings, tech artists from around the world. It is 12:30 Eastern Standard Daylight Time, and it is the East Coast. And that means it's time for another episode of Tech Art Talk Live. Had to think there for a moment there which program we're actually talking about here. But anyway, my name is Chris, and I'm going to be your host today for today's lesson. Now, last week we got an introduction to, or the basics of tech art physics. Now, you don't need to be Einstein in order to be a tech artist. And in fact, you don't need that much physics at all. But you do need to have an understanding of a little bit of physics. Why, you might ask? Well, if you're going to be doing visual effects, you got to understand a little bit about physics, like how stuff falls and why does stuff drop and so forth, and what's friction, and what are forces and things like that. Those are very important for creating any kind of simulation, including particle simulations and or just about any other kind of visual effect that actually kind of duplicates some kind of reality. And also you need it for things like rigging and animation, which are all very important as well. Now, do you need it so much for pipelines? Not so much. Do you need it for shader writing? I don't think so. But, however, having this little bit of extra physics knowledge is definitely not a bad thing. So, last week we started off, we went through some of the basics, and we're going to continue this week with showing about the rest of things, and things will wind to a well-oiled halt here, I think, in just a bit. So we are going to get things rocking and rolling here. All right. So let's get going to the actual lecture. Okay. I'm just kind of reviewing this because I myself forget, and so I like to try to keep track of everything. There are 5 basic equations of motion that you need to keep track of. And this first one is that the final velocity equals the initial velocity plus the acceleration times the time. That gives you the constant or the average or acceleration. And then the average velocity is really just the averages of your first velocity and your second velocity. And you add them up together, you divide by 2, and you get the average velocity. That's nothing too hard. Well, okay, if you wanted to get the amount of space that you moved over during that time, it's just the average velocity times the time, and that'll give you a change of position. All right, well, that's kind of obvious. Now here's where things really get juicy, is that suppose you wanted to get the position relative to its acceleration. Well, you got to take the initial velocity multiplied by the amount of time there, plus half of the acceleration times the time squared. Now remember, we're talking about units here, and so we have to go time times the time. So that gives you the change in position with respect to acceleration. And then if you wanted to get the change of position based on the change of velocity and acceleration, then you got to use this formula where it's VF squared minus VI squared over 2A. Okay, and that will give you the position relative to velocity and acceleration. All right, remember, because we're doing this motion, we're in a 3D world now, right? So we got to do with, we have to do things 3 times. That means that we are probably going to do our velocity, and there is our change of position, and our change of position with respect to acceleration. So we have to do it with vectors. And that means that we got to do it for x, we got to do it for y, we got to do it for z. And then we're going to be doing that for the acceleration, the initial velocity, and the final velocity. Now t is not a vector. T is always going to stay a scalar. So it's going to stay as just one single number. All right. Now, a lot of times when we're dealing with physics, we're dealing with the actual components of projectiles. So there are two kind of things that we have to worry about, and that is just assume that gravity is always constant. And in this case, the acceleration due to gravity is negative 9.8 meters per second squared. And then the velocity is of y, I mean going up and down, is basically your initial velocity plus the acceleration times the time. And then the change of position is a variation of that same equations of where we have our initial velocity times the time plus half of the acceleration times the time squared. All right, those are pretty standard. But even it gets easier than that, because when we have to deal about the horizontal components and the vertical components. Oh, I say we just got finished with the vertical components. Now the horizontal components, let's just assume that once we're dealing with objects traveling in a plane, let's not worry about the acceleration going sideways, because we're just going to say, okay, the acceleration of that is 0. We didn't lose acceleration, we didn't gain acceleration. Yes, I know that we're going to be gaining and losing acceleration due to air density. However, for our calculations, we're just going to ignore them. And so the change of our velocity is nothing but a change of position over time. And that's nice and simple. So that's all we have to worry about. Okay, now today's lecture, we're going to start to learn about Newtonian physics. Now, what is Newtonian physics? Well, it's a combination of Newton's laws. You say, Newton's laws? And you say, yeah. Newton had 3 of them, and we're going to go over 3 of them. And then we're going to go over the physics engine, because this is how all physics engines basically behave, to this basic thing. And knowing how Newton's laws applies to the physics engine really kind of puts everything together. And it really also to do with applied forces. And we'll get onto that in a little bit. And then we're going to talk about a little tiny bit about advanced topics. But really, advanced topics are advanced. So I'm just really going to be telling you about them, not really going into the gory details about them, because if you're worried about advanced topics, then my friend, you understand physics better than I do. All right, so let's get going with Newton's laws here. Now, Newton, he had a first law. And the first law is that ultimately is that an object that's just sitting there is going to stay sitting there. And if an object is moving, then that object is going to keep moving. That is, the object is going to stay stationary, or it's going to keep moving unless there is some kind of force put onto it. Now, we know we haven't talked about what forces are and so forth, but let's just assume that. So if an object is just sitting there, it's going to keep sitting there until someone puts a force onto it. And then the force is going to make that object change position or whatever. It's going to move, accelerate, you name it. I'm not sure. All right. Also, if there is an object that's already moving and it's always cooking along there, that object is going to keep cooking along. Imagine like that object is like in space and it is just rolling around. It's going to keep rolling around there forever because there are no forces out in space. There's just nothing. It's the vacuum. So therefore, it's just going to keep on going on at infinitum. So that's Newton's first law. The second law is actually kind of easy. Force equals mass times acceleration. There's really not a lot to that. And that's kind of like the equation of Newton, because everything else kind of derives from that. Just remember, force equals mass times acceleration. Not too hard. The third law is a little bit precarious, and this is where all the diciness comes in, but it's actually kind of really important. And ultimately, I'm going to say this a couple times. Newton's third law is saying that the forces are neither gained nor lost. They're just kind of transitioned. In other words, when we have one object, it comes in contact with another object, then the forces that those two objects interact with each other, well, they cancel each other out. In other words, for every action, there is an equal and opposite reaction. So therefore, if you hit an object, that object hits back with the exact amount of force and go with that. Now, if one object is bigger than another, and this force hits this object with less force, well, then that object is going to get pushed backwards. However, if this force is going to hit this object, and this object has a really large amount of force, well, when this object hits it, it's going to bounce backwards. It's going to ricochet, and it's going to kind of reflect off of that. And anyway, that's Newton's third law. Every action, there's an equal and opposite reaction. I guess that's the conservation of energy and all that kind of goodness. I mean, we'll kind of go into that just a little bit later. Okay, so there are the three laws. That's really all Newton said. That's all he did. So Newton's was pretty smart. So in order to kind of celebrate him, they kind of named a unit of force after Isaac Newton himself. And 1 Newton equals 1 kilogram per meter per second squared. So in other words, a Newton is the amount of force it takes to move 1 kilogram 1 meter over a second squared. Now what a second squared is, I do not know. Sorry gang, don't know everything. But if you were to translate that from metric to English units, well, guess what? Pounds? Pounds are units of force. They are not units of mass. Kilograms are in mass. Pounds are units of force. So therefore, 1 Newton equals 0.2248 pounds. I bet you didn't know that. Ha 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 ha. All right. Now let's talk about physics loops. Why are we worried about physics loops? Well, the physics loop is what you got to deal with on every single day whenever you deal with anything with physics. If you deal with particle systems, you're dealing with the physics loop. If you're dealing with a simulation, you're dealing with the physics loop. Anything to do with any kind of stuff that's moving that's not keyframed is dealing with the physics loop. You're probably going, really? This is going on in the background? Yes, it is. So every time that you crank up the particle generator, every time that you drop a ball and inside of your graphics engine and it bounces down the stairs, it's going through this physics loop over and over and over again. So what is this physics loop? Okay. It applies to all things like rigid body dynamics. So like when you drop that ball and it bounces down the stairs, then that is part of the rigid body dynamics. And so really, the physics loop deals with the animation of all non-deforming bodies. Now that's very important because the physics, when dealing with rigid body dynamics versus deforming bodies, is the same, but it's simpler. So rigid body dynamics is like pretending like everything is a particle and everything is just bouncing off of each other. And therefore, it makes the calculations kind of go easy. All right. Now, in simulations where objects do react to each other, okay, it's basically all simulations where objects interact with each other. Yeah, okay. So the physics loop actually does apply when you're creating deformed objects too, but deformed objects are just a little bit more complicated, and there's more math involved with it. But here, let's take a look at what this physics loop actually looks like. All right, now this kind of goes round and round in circles, and it keeps going on all day long. But really, this is the kind of the behavior that we're talking about here. At the very first thing that happens is that the forces are applied. Okay, remember what a force is? Like, so if you're going to smack a ball with a baseball bat, that is a force. So you're going to apply that force. If you are going to step and move your body forward, well, that process of stepping is putting a force of your foot against the ground. If you are pushing your body forward, then you're launching off the wall. If you pushing against the wall, that is a force. So you're applying those forces to the system during the first step. During the second step, then you have to update. Okay, when a force is applied to the system, things move, right? Remember Newton's law? First law, an object at rest tends to stay at rest until there's a force applied to it. Guess what? There's a force applied to it, things start happening. And sometimes that might even stop. So therefore, that's what happens during the second step. We update the system. We have those forces applied. Then, pretty much whenever you have a force applied, you're going to have moving objects. And objects tend to bump into each other. That's right. And so therefore, we have to identify where all the collisions are going to happen. Now, we don't have to actually process them all, but we just kind of have to figure out where are those collisions and what can possibly happen. And is the object colliding? Because if the object actually was colliding, what would happen? Newton's third law, that's right. It would apply in a force backwards. But we're not going to deal with that until we go back up to the first step again. So we're just going to detect all the collisions. Now, there are certainly these gizmos that are in the physics loop called constraints. And a constraint is a relationship of one object to another. And I know that that's vague, and I apologize, but that's the best way that I can put it. A constraint is something like, okay, suppose that you have a car, and a car is sitting on a ground. And so the car and the ground are related to each other in such a way that the car can only move in one axis along the ground. It can go forward, it can go backward. Now, if you turn the wheels, that kind of changes things a bit, but as just rolling around the car, like imagine it's just a go-kart, or it's a kit car, it just goes forward, it goes backwards. Therefore, it is constrained to the x-axis, and that's an example of a constraint. If you have a look of your elbow, the elbow is constrained to revolve around the z-axis of your arm. If you have your shoulder is constrained to rotate in all three axes, but its translations are denied. So therefore, you're constrained to only the three rotations, but there's no translations. And then, once those constraints have been resolved, then what you got to do then is let the system display the results. Okay, so all this activity goes on, but we didn't actually see any of it happening until we go to the fourth stage, or the fifth stage, and that's where the results are displayed. Once the results have been displayed, we start over again, and then we start applying all the forces that got generated during the collisions and the constraints. You see? Nice big old loop. So that's very cool. So where are these forces, though, that we have to deal with? Well, there are a whole buttload of forces that we have to deal with. But for the most part, we're talking about applied forces. And the applied forces that we're usually dealing with there's four forces here. Now, there's a whole bunch of other forces that you're dealing with, especially when dealing with aerodynamics, because you got to deal with drag, you got to deal with lift, and that applies to anything to doing with water. And there's just like a whole bunch of other forces to deal with, but normally we're dealing with just four of these, and we're dealing with weight force, active force, normal force, and then friction force. So what are all of these forces? Well, I'm going to go ahead and demonstrate that right now. Okay, weight force. Now this one's kind of obvious. Now this is the force that gravity is pulling us. Remember, gravity sucks. And where is it? It's sucking us right to the center of the earth. That's right. So gravity is a weight force. And so the weight force is actually gravity pulling us downward. So gravity is a force, and it's pulling us down towards the center of the earth. And so therefore, the force is a vector, and it has a direction, and it always goes down. Now, usually that vector is, well, let's just say it's 0, -1, 0. Usually, that's what the direction is. Now, it doesn't have to be that way, but it does change. Like if you're no longer on a flat surface, if you've got on a ramp, then suddenly, then you have to change that weight force. The weight force is now pulling down, and that ramp is kind of like going at another angle, and so therefore you have to kind of figure out the cosines and the sines and the tangents of that weight force. We'll kind of go into that a little bit. So let's just say that weight force is just 0, 1, -1, 0, only when the surface is flat. Okay, and so that the weight force equals mass times gravity. So that's Newton's second law, remember? It's mass times acceleration. That's force. Okay, so weight equals mass times gravity. Gravity is an acceleration. That's right, gang. All right. Where, okay, we've got that. Yes, yes, yes. Mass and gravity of 9.8 meters per second. Now the active forces, now these are the forces that you or your buddy or the world is applying against your simulated object. Okay, the important thing to remember there is when all things are moving, they're accelerating. They're either accelerating in one direction or another. They're either going accelerating this way or that way. Objects very rarely have the same constant acceleration. So objects are either decreasing in speed or they're increasing in speed. It's just usually the way it is. And so therefore the active force has to be in parallel with the acceleration. That's an important thing to consider. Okay, so we've got the acceleration. It's going from left to right in this example. And so we've got a fellow who is pushing on there. So this first green arrow is actually applying force in the direction of that, or he's pulling, and therefore his active force is pulling in the same direction. Now notice that the change of the position is different between the pushing and the pulling. The guy is like either in front of the object or behind the object. But notice that we have those two green arrows. Those are the active forces that are pulling against the object. And so those are the active forces and they stay the same. Okay, yeah, pushing and pulling. We got that. Very good. Okay, what are then normal forces? Normal forces are the forces that a surface pushes against an object that opposes gravity. All right, so remember that the Earth is sucking you, trying to get into the center of the Earth, right? But the ground is saying, no siree, Bob, we're going to prevent you, mean Mr. Gravity, from pushing Mr. Tech Art Teacher through the ground here. So the ground is actually pushing up in the opposite direction that gravity is pulling you down. Remember we were talking about it's not the force, it's not the speed that kills you, it's the splat. Well, that splat is the ground saying, no, we're not going to let you go to the center of the Earth. We're going to push against you. Okay, so notice that the normal force is in the exact opposite direction of the weight force. And that's pretty much all that there is. And so it's got to be perpendicular to the surface and going in the same direction as the weight force. In fact, the normal force is actually equal to the negative weight added with all the other forces. So that means if you were to go and push against the block and push down on the block, and so basically you're working with force in order to push that block onto the ground, well then the ground is forcing, its normal force is kind of going not only the weight of the object, but the weight of you pushing down on the object. So it's a negative force. So it's the summation of all of those things. It's the addition of the weight and all the other forces pushing down, going along with gravity, and it's the negative of all those. So it's kind of like going in the opposite direction. So that's the normal force. Okay, and normal forces are perpendicular to the acceleration. Look here, there's the acceleration, and it is going up along the path of this incline. Now here's our active force that we're pushing against the object. Now notice this fellow, he's pushing down at an angle. So therefore we have to break this angle, this force, into two other forces. And those forces are parallel with the acceleration and perpendicular to the acceleration. And likewise, for the weight force also has to go either parallel to the acceleration or perpendicular to this acceleration. And so therefore, in this example here, we have, if we wanted to go and figure out what the normal force is, we would have to add this arrow here, which is the weight force that is perpendicular to the acceleration. And then we'd have to add it to the push force that is downward, and that's also perpendicular to the line of acceleration. So these things get a little bit dicey because then you're going to have to use sines and cosines here to actually figure out how does this vector project onto this axis and so forth. So that's a little bit to extra consider. All right, so there it is. Normal equals the weight force of y. And no, I said y. This would be the y of the weight force. This would be this arrow here. Plus the active force of y. And notice here that would be this arrow here. So notice that both of these arrows are pointing down. So therefore the normal force is the exact opposite of the combination of those two. And that's why it's going in the opposite direction. All right. Now what is friction? Now friction is when two objects are interacting with each other. Then the friction is the force that either slows one object from interacting with the other object or prevents an object from moving when it is in contact with another. And so therefore they have these things, they call these omicrons or microns. I can't remember what the actual Greek name for that is omicron, I believe. But anyway, they is the coefficient of friction. And you say, like, well, how do I figure out what these coefficient of frictions are? If you go out into the internet, you can just look up coefficient of friction for rubber on ice in order to figure out how a car is going to skid around here. And they'll give you this number, and there's actually a measured number, coefficient of friction. But anyway, the friction force is the coefficient of friction multiplied by the normal force, and you're going to take the negative version. So it's negative of the normal force multiplied by the coefficient of friction. Okay, now there are two types of friction. There's static friction, is the friction that prevents two objects from moving with each other. So before an object starts moving, there's the static friction. And then once the object is moving, then you have the kinetic friction, and that's the friction that slows the object once the move had started. But notice here that the two formulas are exactly the same. Whether you have the force of the friction either static or it's kinetic, it equals to the coefficient of static friction or the coefficient of kinetic friction multiplied by the normal. So static friction and kinetic friction, although those are two different critters, they look and behave basically the same way. So notice here we have this, the force equals the coefficient of friction times the normal force. And so here it is. Here's our normal force. It's pointing up against that. And so it's pointing, here the friction force is kind of going perpendicular in that direction. So yeah, notice that the friction force is always perpendicular to the normal force. Something to remember. Okay, now net force is important because you got to try to figure out, okay, now we're dealing with the acceleration. What do we do with all those forces? Well, we got to try to add all this up. Now the net forces is what gets applied to the physics loop during the first stage. You know, when it applies to all the forces, well, it's applying the net forces. And so this is why we have to figure this. So what we have to do is understand where the object is accelerating. And then we have to figure out what its active force is, what its weight force is, what its friction force is, and if there's any kind of other forces at play there. Then we got to go and add them all up. And so it's got to, remember, it's got to be in the direction of the acceleration. So in this particular example, not for everything, what we're dealing is with the active force here going with the weight force, which is going there, and it's added with the friction force. Now you're probably asking, wait a second, the weight force, that sucks stuff to the ground, into the center of Earth. Why aren't we dealing with the little arrow kind of like going here? Well, we are dealing with the little arrow, but remember, because this arrow is pointing straight down. But what we have to do is deal with the forces of acceleration that are in the same line as the acceleration. So remember that this little arrow that points down is actually broken into two arrows, one that's perpendicular to acceleration and one that's parallel with acceleration. And because we're dealing with just the stuff that's parallel with acceleration, we don't deal with the vertical component of the weight. So therefore we're just dealing with the horizontal or the parallel version of the weight force. So therefore, in this situation, our total net force is the active force added with the friction force added with the weight force. Notice that these two arrows are pointed in the opposite direction. So whether they cancel out each other, I don't know. It depends. Now check this out. If the active force equals the friction force and the weight force, if they equal each other, then the object is not moving. The acceleration is zero. So the net force is going to be zero. However, if it is moving, either the box is sliding down the hill and the guy isn't pushing hard enough, or he's actually succeeding pushing the object up the hill, then therefore, if he's pushing it up the hill, then the active force is going to be greater than the combination of the friction force and the weight force. And if it's falling down the hill, then the active force is less than the friction and the weight forces combined. All right, now I know that that's a lot to consider, but that is how we evaluate all of the forces during the friction loop. Okay, now we do have to deal with collisions, because that's the third step of the loop. And so we collide against one object against another, right? So one object is bouncing against the other. So we have to figure out how do things bounce against each other, because then we're going to have forces and velocities, because the velocity is going to change. And I forgot, there's a name for this law, but I can't remember what it is. My apologies. I should have looked it up, but I didn't even think to. But anyway, the angle of incidence equals the angle of reflection. So in other words, if we have this ball and it's careening, it's going to slam against the wall right here, notice that it has an angle here. And that's the incoming is the angle of theta. Now when this ball hits and then bounces off here, it's got a reflection angle. By necessity, we have a certain law here. The angle of incidence equals the angle of reflection. It means this angle here is going to be the same angle of once it reflects. That's just how things work. And so if we were to look at it kind of like in a sort of way, we have, if we are to break the incoming velocity, we would have the incoming velocity of x going like this and the incoming velocity of y going up like that. Well, therefore, after it's reflected, then the y velocity keeps going that way and it stays the same. But the x direction kind of goes in the opposite direction. So it kind of like goes and boogies off in the other direction. So the y stays the same and the x stays the same. Now, if this was a horizontal collision and just bouncing off the ground like that, then the x velocity would stay the same, and then the y velocity would flip just like that. Okay. And so actually that's what we're talking about. And we were talking about that. I really should have a diagram for this. But anyway, this is just reiterating what we showed before. And the important thing to remember is that the incoming velocity is equal to the outgoing velocity. Okay, so what do we deal with when the thing isn't flat? Now, if the wall was vertical, it's nice and easy to compute, but if it's horizontal, it's not it's easy to compute. But what if it is something arbitrary like that? So what do you do with that? See here, the velocity of the incoming equals the velocity of the outgoing. So it is still the same, but suddenly the vectors are not so convenient to work with. Well, there's a formula for that. So the final velocity of this object is 2 times p, and it's going to be dotted with n plus the initial velocity. Oh, that's a headache. I should have had my Houdini thing. In order to test this formula out, I actually put this in Houdini and got it working, and it actually does work. It's kind of amazing. But anyway, suppose here's our incoming velocity coming in like this, and then we're going to go, we're going to add that with, we have this p, which is actually this kind of like vector here that is trying to figure out how much does this vector project onto the normal of this. So if we have 2 times p, so basically if this is p and this is double p, so that's 2 times p times n, it's going to be dotted with the n. So it's going to be some kind of value there. And then we're going to add that to the I direction. And what we have here is the new velocity going to be right here. It's a kind of a nifty formula. If you ever have a chance to play around with it, I encourage you to check it out. It's a lot of fun to play around with. All right, now let's deal with advanced topics. Now, advanced topics, like I said before, are advanced, and most of the time tech artists don't have to deal with them, because then you're either like, if you really know what you're doing, then you're probably not listening to this lecture in the first place. But I'm just going to include these along just in case you were ever curious. Okay, we have this concept called work, and that is force times distance. Okay, so if you were to apply a force over a distance, that is the amount of work. There you go. And there is energy then. Energy is broken up into static energy or kinetic energy, kind of like friction. Okay, kinetic energy, when an object is moving, it's the amount of energy an object has because it is moving. Okay, so the kinetic energy equals one half of its mass times its velocity squared. Okay, that's just the formula. That's the kinetic energy. Okay, now you have potential energy, and that is the energy stored up in an object due to its height off of the ground. Now, the potential energy when it's due to the height off the ground is actually called gravitational potential energy. So when you're just dealing with potential energy when things are going up and down, once again getting sucked to the earth due to gravity, that's called gravitational potential energy. But in this case, we're just saying, okay, if an object is at rest, but it stands getting ready to go into action, that is basically called potential energy. And so it looks very similar. And so that the potential energy is this mass times gravity, but you also have to multiply it by the height. So here you have mass, is like you have a ping pong ball or a bowling ball, and then you've got to multiply it by gravity, and then you got to multiply it by, okay, this bowling ball is on a platform. It is a meter of the ground, so therefore that would be 1 meter times gravity times the mass of the bowling ball. That'll give us the amount of potential energy. Okay, that's all good and fine, but the important thing is, remember how we were dealing with Newton's third law, and we were saying, okay, fine, for every action there's an opposite reaction? Okay, well, this has to do with the conservation of mechanical energy. And so you have the kinetic energy and the potential energy. If you combine those with after a collision, then you have the kinetic energy after the collision of the kinetic energy and the potential energy after the collision. So before the collision and after the collision, they equal each other. And so that's called the conservation of mechanical energy. And that's a direct translation of Newton's third law. And that all comes down to this gobbledygook here. And all I did was replace the energies here with their equivalent formulas. Nothing really too complicated. But that's just saying that energy stays constant. And it just changes between potential and kinetic energy. So really, that's all that happens. The amount of energy in the world kind of stays the same. It's just getting transferred from kinetic energy to potential energy back to kinetic energy. Okay, and now there are a few other critters that we got to deal with that kind of help implement that, and that is momentum and impulse. What is momentum? Momentum equals mass times volume, not mass times velocity. Now remember, work is mass times velocity squared. Well, if you're just going to give mass times velocity, that's momentum. And impulse is like suddenly, if you're going to apply a whole bunch of momentum or a whole bunch of energy to an object or to a force just for an instance, that is an impulse. And so you have to deal with time. So it's force over time. Okay, and so that kind of deals with it, and there's like little kind of formulas that kind of integrate that all in together. Now, usually T is a very small amount of time, so the amount of force going into the network is usually kind of small, and it's not continuous, and it doesn't compound on top of each other. All right, now if you've gotten this far, then you're either like have fallen asleep and I was just blathering on here, or you actually know more about physics than I do. And if you do, then I invite you to come onto the show sometime and we'll talk about this, because then you can talk all about circular motion. Now, circular motion is the duplicate of everything that we talked about for these last 2 weeks, but instead of going in a straight line, this is like going in circles. And so that's where you're dealing with angles now rather than displacement. Remember how last week we were talking about displacement? Well, now we're dealing with angles when you're dealing with circular motion. All right. That's what I wanted to cover with you today. Not a whole lot of crazy information, but kind of wraps things up and puts things in context with Newton's third laws, and especially how they apply to the physics loop, because the physics loops are something that all tech artists have to deal with one way or the other when they're actually doing any kind of simulation, they're doing any kind of particle work, they're doing any kind of visual effects, or they're working with any kind of rigging. All right, groovy stuff. Now we're going to diverge into a really, really fun topic starting next week. I think I'm going to have at least 2 lectures on this, just because I really enjoy it and you get to hear me blather on it. And we're going to talk more next week. We're going to start talking about ray marching. Yes, folks, that's it. We spent a couple of weeks with ray tracing. Now we're going to deal with ray tracing's kind of like not so smart cousin. You know, everyone, has the cousin that, might not be as smart, or maybe you're the less smart cousin. Yeah, okay. So if you're the less smart cousin, then I am ray marching, and your smarter cousin is ray tracing. So, but actually, ray marching is totally cool, and we're going to start going into ray marching on the 2nd of July. Can you believe it's the 2nd of July already? We're going to start dealing with ray marching on the 2nd of July. All right. Speaking of July, don't forget GDC 21. If you happen to have an all-access pass and have nothing better to do, or maybe you're having trouble sleeping that night, you might want to go check out the teaching sessions. And on the teaching sessions, tune in, because, hey, I'm presenting on there on the 21st at 1:20 Pacific Standard Time. I will be presenting Object-Oriented Python Crash Course using Houdini. That's right. I'm going to teach other instructors out there how to teach your reluctant art students how to program in Python in 6 weeks. Tune in and you'll find out why. All right. So that's really cool. If you like what you saw today, go ahead and subscribe and hit that little button on the right-hand side. Go ahead and subscribe to this YouTube broadcast. Otherwise, check me out. My name is Chris Rhoda. Check me out on Facebook and on LinkedIn, or check out Art EDU, which is also on Facebook and on LinkedIn. And if you get around to it one of these days, go and check out the website, techartedu.com. And on that website, you'll have a chance to go ahead and press the button, and you can opt in. And then when you opt in, leave me your email address, then I will send you updates whenever Art EDU has any more information to describe and go forth. Okay, gang. It was fun dealing with physics with you for the last 2 weeks. Next week, we're probably going to spend 2 weeks dealing with ray marching, which is a whole lot of fun too. So stay tuned. Starting next week, we'll be dealing with ray marching. All right. Thank you very much for joining me again, folks. I look forward to talking with you again next week. And until then, arrivederci.